Okay, good morning everyone. Good morning. Okay, good morning. Quick announcement. I think I emailed this as well on Carmen, but I've postponed your homework due date by 1 day because apparently I came to realize that Sunday is Easter, so it's a bonus of a day. Okay? So it will be due on Monday, 11:59. So today's lecture we will complete the boundary layer analysis. We will come up with the final expression for the heat transfer coefficient, and we will forget all of that has happened in the past 3 lectures. Okay? All right. So I'm going to start off from where we left off last class. And what I want to do in the next week and so, I think we have around 4 lectures left, not including today. I just want to spend time solving problems on convective heat transfer during those 4 lectures. I don't think learning new material is any useful because the basic idea remains the same. You just need to obtain the heat transfer coefficient. If you know that, then it is just a question of using the energy equation and solving things. Okay? All right. So today we'll complete everything. I will call it a day, maybe in 45 minutes or so. So from last time, continuity. du dx dv dy is 0. This is the simplified version of what we looked at last time. Then the momentum equations. There were 2 of them. Okay, this is the simplified version. Is u du by dx v du by dy is minus 1 by rho dp by dx, and then mu by rho d square u dy square. We are doing this for flat plate flow, by the way, 2-dimensional. And the second momentum equation is u dv by dx dv by dy 1 by rho dp by dy, and mu by rho d square v by dx square. And these are once again the simplified versions of these. And then the last one was the energy equation. U dt by dx v dt by dy is kf by rho c d square t dx square d square t dy square, the Laplacian of the temperature or the heat diffusion equation on the right hand side. Then we said that this all came from some simplifications of the typical Navier-Stokes equation. Then we said that we will non-dimensionalize all of these. And the reason for doing so is because we figured out that the temperature is a function of 12 parameters if we look at these equations here. Okay, we discussed those things last class. So non-dimensionalization, I want to write it down because we're going to use it again. So here are the parameters. So u star is u by u infinity, u being the velocity along the x-axis. Okay, so flow velocity. This is x, this is y. This is velocity v. And then we have v star is v by u infinity. Then we have x star and y star. X by L. Y star is y by L. And then two more non-dimensionalizations, the pressure, P, I'll write it out here. P star is P by rho U infinity square, which also has units of pressure eventually, and then temperature T star is T minus Ts by T infinity minus Ts. Okay, so these are the non-dimensionalized pressure, temperature, distances, and the velocity variables. And I posted on Carmen the entire process of taking these, plugging them into these respective equations. Please take a look at it. I'm not going to do it. I'm going to write the final form of all of the non-dimensionalized equations. Okay, so which is what we're going to be working for today. So substitute into the governing equations. And this is what we end up getting. Equation 1, which is a continuity equation. Its form remains the same. It's going to be du star by dx star dv star dy star is equal to 0. So no changes there. This satisfies the fundamental form of the continuity equation. The momentum equations, or the force balance equations, they end up looking in the following way. U star du star dx star v star du star by dy star is, the density term will vanish, and this will end up just being dp star by dx star. Please consult if you're interested the notes that I've posted on Carmen, where I've showed the dimensionalization, non-dimensionalization. Excuse me. And then I have 1 by Reynolds number. Reynolds number over the length of the plate. Okay, and we are assuming laminar flow here. And this is going to be d square u star by dy star square. So this is the second equation. Third one is also from the momentum conservation. I'll just write it out below. So u star dv star dx star v star dv star by dy star is minus dp star by dy star, 1 by Reynolds number, d square v star by dx star square. And I partially showed the energy equation being non-dimensionalized. This was the fundamental form of that. U star dt star dx star v star dt star dy star, and then when we perform the non-dimensionalization of the energy equation, we end up with the combination of the Reynolds number and the Prandtl number. So this is 1 REL PR is the Prandtl number, okay, and multiplied by d square t star x star square d star by dy star square. And if I look at the dependence of the temperature now, previously it was 12 of them, okay. I have half a mind to write it out, but I hope you take my word for it from the previous lecture. So there are 12 of them from the last time. The variables here, you will see there is u star v star. Obviously the last equation has x and y stars, So put those things too. Then I'm going to have the Reynolds number. Prandtl number and pressure, of course, P star. So this is partially good news. I went from 12 dependencies to 1, 2, 3, 4, 5, 6, 7 dependencies. So at least there is some hope, right? So there are now 7 dependencies here. That is still one too many for us. So we have to go through the last layer of reduction, okay? And that's where I've kept spaces for these. Alright, so the culprit here is this pressure term, because that we have no idea what the pressure is within the boundary layer. Outside the boundary layer, of course, the pressure is free stream pressure, P infinity, whichever is the one that is the flow pressure that is prescribed to begin with. But within the boundary layer, this can fluctuate wildly. The fluctuation of the pressure is the cause for, in many situations, transitions from laminar to turbulent flow, as you might know from a flow past a cylinder and so on from fluid mechanics, and even flow past a flat plate. So, I somehow, by hook or crook, I want to get rid of this guy from my equations. And that is a whole plan for the next 15-20 minutes. Okay? So what we are going to do next is called as an order of magnitude approach. So plus order of magnitude approach. And in all reality, this is a part of a course like intermediate fluid mechanics. So we don't go too much into the details of this in heat transfer, but I believe that it is okay to present at least 3/4 of the story, rather than just present to you no story at all. I will obviously not end up showing you how to solve the boundary layer equations. We are just going to look at the final solutions. Those are solved by numerical integration. But I also at least want to present to you the final boundary layer equations. It's a seminal point in history. Okay. All right. So how to do this order of magnitude approach is the following. Look at this. Let's start off with x star. What's the range of x? X goes from 0 all the way to the total length of the plate. All of you agree with me on that? So when x star is 0, when x is 0, x star is 0. When x is L, x star is equal to 1, which means that the maximum value of x star is 1. And if I think of dx star, which is the difference between the minimum and the maximum value, so this is an order of magnitude analysis. So, excuse me, dx star is going to be the difference between the maximum value and the minimum value, so that's also going to be equal to 1. Does this make sense to everybody? dx star is nothing but the difference between the maximum and the minimum value. So this is an order of magnitude analysis. So we say that dx star is on the order of magnitude of 1. Okay? Or dx star scales as 1. What do you know about y star? Obviously when y is 0, y star is 0. What's the maximum value of y? Within the boundary layer. It's the boundary layer thickness. So when the value of y is equal to the boundary layer thickness, I have something nice going on. See, when y is delta f, Typically, the fluid boundary layer thickness for us is more or less going to be thicker than the thermal boundary layer thickness. So I'm taking an order of magnitude approach here, taking the larger of the two, so that Y star is delta F by L. Delta F is the boundary layer thickness, which is very small. L is the length of the plate, which is typically very large. So I'm going to call this ratio as epsilon. So Y star is equal to epsilon. And if I now take the difference between the maximum and the minimum value of Y star within the boundary layer, this scales as epsilon. So d Y star scales as epsilon. I want to see if this makes sense to everybody. You understand the scaling procedure, right? You have the maximum, you have the minimum values within the boundary layer. This is what is happening here. So this scales as epsilon minus 0, so that's epsilon. Do the same thing for U star and V star. So when U is 0, U star is 0. Within the boundary layer, at the edge of the boundary layer, U becomes approximately equal to U infinity. So at the edge of the boundary layer, U is approximately, or 0.99 times U infinity, so U star is approximately 1. Which means du star, the maximum minus the minimum value, scales as 1. And the maximum U star is approximately 1. The problem is this. I have no idea what V is going to be. So I just leave it aside. Okay? Don't touch it for the time being. I also have no idea what the pressure is going to be within the boundary layer. I know outside the boundary layer it's going to be the free stream pressure, P infinity. Within the boundary layer, God knows what it is. So, let me focus on temperature. At the surface of the plate, T is equal to Ts, so T star is 0. At the edge of the boundary layer, the thermal boundary layer, T becomes T infinity, so that T star is equal to 1. The difference between the maximum and the minimum is the scaling of T star, so d T star scales as 1. So this is a big question mark. This is also a big question mark. And our whole aim is this, okay? So somehow, if I can come and say, all right, forget this dp star by dx star, forget dp star by dy star, well, forget this entire second equation here. Let's just throw it out of the window. Do something similar here and get rid of this guy, as you will see. What you will have at the end of the day is a partial differential equation in x and y. For u and v, I'm going to have two equations, the continuity and one of these equations. For temperature, I'm going to have a PDE that I'll solve from here. The solution of the first two gives me the boundary layer thickness. The solution of the third one gives me the convective heat transfer coefficient. And the solution of the first two is perhaps what you may have seen in fluid mechanics as the boundary layer equations. And I'm not sure if they have done this in fluid mechanics. So is that the case, or is it too much of a past history that you would like to forget? That's fine. You'll see it here again. So. All right. So let's start on our journey. Here is what I'm going to do. Take the continuity equation. Then, instead of du star, I'm going to substitute the scaled value or the maximum value of du star. Instead of dx star, instead of dy star, I'm going to do something similar. Instead of dv star, I'm just going to leave it like that because we don't know what it does. So, and I'm going to say the following as well. So if I take the magnitude, is equal to does this make sense to everybody? It's from the continuity equation. du star scales as 1, look at that there from the first panel, so that's 1. dx star scales as 1 as well. dv star, I don't know the scaling, so I just write it. dy star, as you know, scales as epsilon, which is written down in the first panel, which tells me, if I look at an order of magnitude estimate, dv star scales as epsilon, because this side has to be equal to that side. Okay, so dv star scales as epsilon. And if I look at v star, which is v by u infinity, I obviously know that if dv star scales as epsilon and the initial value of v star is 0, so at v is equal to 0, v star is equal to 0, I know that the range of dv star is epsilon, so that the maximum value of v star this is because dv star is v star max minus v star min. Okay, so does this make sense to everybody? Once again, I'm taking the continuity equation. Rather than write it as something plus something is equal to 0, I'm just looking only at the magnitudes because I want to understand how much of it is scaling by. This is du star, which is 1. dx star is 1. I don't know dv star, but dy star we found out that it scales as epsilon. So from this I figure out that dv star scales as epsilon. Minimum value of v star is 0. What's the maximum value? Just going to come from here, which is epsilon. So this is done. Let's now take a look at equation 2a. This is 2b. And we're almost there. So if I look at equation 2a, let's start writing all the scaling. So u star is 1, maximum value. Wherever you see a u star or v star, just put their maximum value, okay, because it cannot be worse than that. du star by dx star is 1 by 1. V star is the next item. Maximum value of V star is epsilon. du star by dy star. du star is 1 maximum. dv star is epsilon. This is equal to I can put a negative sign, but it really does not matter. I'm looking only at magnitudes plus the Reynolds number. And watch this. d square u by dy square is d by dy star of du star by dy star. This is from the basic definition of differential equations. Scaling now, we don't worry about this guy. We worry only about the scaling of dy star, which is epsilon. Scaling of dy star once again is epsilon. Scaling of du star is 1. So this becomes 1 by epsilon square. Okay, so we are looking at the scalings of these things. Which is fed in there. So if this is the case, then all I need to do is, okay, to look at the scaling of dp star by dx star, I need to look at the right hand side. The right hand side has to be the same as the left hand side, which means that dp star by dx star has to scale as 1, and this entire set of terms here have to scale as 1, which means the Reynolds number scales as 1 by epsilon square. So the Reynolds number is not a small quantity, it's a fairly reasonably large quantity, but still less than 10 to the power 5. So this tells us dp star dy star scales as 1, and the Reynolds number scales as 1 by epsilon square. Almost. 2 more things to do. Equation 2b. This is where we start doing some big time cutting. U star dv star by dx star. U star is 1. dv star by dx star is epsilon by 1. dv star is epsilon, dx star is 1. V star dv star by dy star. V star is epsilon. dv star is scaling as epsilon. dy star also scales as epsilon with a plus sign. Here. Scaling of dp star by dy star. You can put a negative sign if you want. Not really needed. 1 by Reynolds number, so that scales as epsilon square. And then d square v star by dx star square. That scales as epsilon by 1 square. Write it as the following, so I'll rewrite it here. Is d by dx star, is, and that's the scaling. Make sense to everybody? In some vague way at least, you see what's going on. Now I'm going to start cutting off. That's epsilon cube. Very, very small. Goes for a toss. Then I just compare the terms. There's 1 epsilon here, that's gone. dp star by dy star from an order of magnitude analysis has to be at least epsilon. So it scales as epsilon. This is a huge conclusion with a lot of heavy hitting. And so we come to the following bigger conclusion that dp star by, this is dx star, I'm sorry. dp star by dx star scales as 1, dp star by dy star scales as epsilon, so that epsilon is much smaller than 1. So I'm going to neglect every equation that has this particular term. Okay, so from this we conclude this is much smaller than dp star by dx star. And we also say the following: equation 2b, at the minimum each and every term scales as epsilon. Equation 2a, at the minimum each and every term scales as 1. So equation 2b is not as dominant in the scheme of things compared to equation 1b, equation 2a. So I'm going to cut off that equation. With your permission, I'm just going to slide this down. So this whole thing is now going to be removed. Once again, why am I doing that is because if I compare equation 2a and 2b, equation 2b sitting here, equation 2a sitting there, All of the terms in 2a scale at least up to 1. All of the terms here scale at least up to epsilon. Epsilon is much smaller than 1. Get rid of it. More interesting things now. So get rid of two b. And I want to show this one more simplification, and then I'll have a couple of shortcuts. Flat plate. This is the boundary layer. Okay, so this is boundary layer flow. This is Y. Outside the boundary layer, the pressure is always constant free stream pressure. So, if I'm sitting at the edge of the boundary layer, the pressure is P infinity. Does this make sense to everybody? Everywhere else the pressure is the same. So the fluid is flowing past, and so the pressure here is P infinity, and so on and so forth. Within the boundary layer, the things are taking place, we don't know what they're doing. At some x location. What do we know? We know that dp star by dy star is negligible, right? We just figured that out. dp star by dy star scales as epsilon. Epsilon from the point of view of order of magnitude is quite negligible. And if dy star scales as epsilon, dp star is actually epsilon squared. Okay? So if dp star by dy star is negligible, what it means is that at a given x location, the value of dp star by dx star is the same all through. Does this make sense to everybody? And maybe I'll write this down. So at some x location, value of dp star by dx star is same for all y. Because there is no variation in y, so obviously the values are all the same through all the y's. There is no secret to this. At the edge of the boundary layer, so I guess let me write this out. So this is y is equal to 0. Y is equal to delta f. So dp star by dx star at y is equal to 0 is because dp star by dy star scales as epsilon, or this is very, very small. Okay? And this is the big leap that we're going to make. We've made many leaps. At the edge of the boundary layer, what is the pressure? At y is equal to delta f, P star is the pressure at delta f. Rho times u infinity square. I'm just copying down the expression from the first panel up there. Okay. What's the pressure at the edge of the boundary layer? This is just P infinity. Which is the free stream pressure. Free stream pressure is a constant. U infinity square is a constant, rho is a constant, which means dp star by dx star at y is equal to delta f is 0. Which means that dp star by dx star everywhere is 0. And so we completely discard that creature out of the game. So now the pressure has gone for a toss, does not do anything to my life anymore. Okay, so this says dp star by dx star is equal to 0 at y is equal to delta f, which means it's 0 for all y. And so I go back to my big equation set there, cancel it off. This is quite nice. And with your silent permission, I'm going to say that something similar will happen to this guy. Okay? That will be posted in my extended notes. And so this is similarly. And so the end of the story is almost approaching. And now our simplified equations are of the following form. So after all the simplifications, continuity is still there. You have to have it. Mass conservation has to be happening all the time. du star by dx star dv star by dy star is 0. This is true. Then I have the second equation, u star du star by dx star v star by y star is 1 by Re. And the last one. Equation 2b is gone. Equation 3, one of those d square t by dx square goes off. So I have u star dt star by dx star v star dt star by dy star is approximately equal to 1 by Re parental d square t star. These are the simplified. Governing equations. And this is called the Blasius-Paulhausen equations. Paul Blasius was a student of Ludwig Prandtl a long time back, and both of them are instrumental in essentially aerodynamics taking place to the extent that we have it today. The Blasius equations are the first two. Paulhausen equation is the third one. In combination, they will help you solve for the boundary layer thickness, the first two. The third one will give you the convection heat transfer coefficient. Okay? And I'm just going to sketch out the solution procedure. I'm not going to go over the details of it. Until now, we have not been spared the gory details. Now I'm going to spare you some. So here is the solution procedure. We typically write this u star and v star, or if you want, you can take this equation and bring it back into the original form, the dimensionalized form. For equations 1 and 2 without the stars. Not necessary, but it can be done, it's not a problem. U du by dx plus v du by dy is mu by rho. If you substitute the first into the second, you get a parabolic partial differential equation, which can be solved numerically, okay? But we don't want to do that. What we want to do is we want to convert it into an ODE. So to do that, we select u is equal to d psi by dy v is minus d psi by dx, where psi is some function. Psi is some unknown function. Psi is obviously a function of x and y. And you'll be surprised, or there's nothing to be surprised about actually. If you take these guys and substitute this back into the continuity equation, it will satisfy that. It has to. Otherwise, there is no solution. Okay? So one can easily check and see that. I'm not going to do that. Then we have the Blasius solution, is the following. By cleverly meaning cleverly for us by looking at the book, for Blasius it was a lot of intellectual sweat. So when we look at it, here is the final form. At least for me, it is just looking at the book. We have actually obtained this. If you take like a higher level fluid mechanics course, they'll derive it. So you select eta is some variable eta. Okay, it is y times u infinity by nu times x to the power 1 by 2. Nu meaning the kinematic viscosity, mu by rho, and then psi is u infinity, some unknown function f of eta, which is what you're trying to solve for, and then so this is essentially a change of variables that one performs. You take all of these fellows, substitute this back into the PDE that you find here. The confluence of all of these factors will end up being the following. So eventually, this PDE will be converted into an ODE, and I have the final form here. It's 2 times d cube eta by d eta cube plus f of eta. I'm sorry, this is df plus f of eta, and this is d square f by d eta square. This is in many ways a very trivial equation to solve for an ODE, okay? Numerically, not a full-blown solution, numerically. ME 2850. Numerically solve this, and interesting things happen now. Hopefully this brings back some memories. You already obtained the solution and so on. When eta is equal to 5, so after solving, when eta is equal to 5, what will happen is that you obtain f of eta and so on from the solution. So we solve for f of eta. Once you solve for f of eta, substitute eta is equal to 5 and obtain the velocity u. We will find that u is approximately 0.99 times u infinity. What is the significance of that? When the velocity reaches 0.99 times the free stream velocity, what's that height called? That's the boundary layer thickness, right? So when eta is equal to 5, I actually reach the boundary layer thickness of y is equal to delta f. So at and this is regardless of where you are along the length of the plate. I could be at x is equal to 20, I could be at x is equal to 40. This is the nice thing about the scaled solution. This is a scaled solution, or what's called as a similarity solution. Wherever you are along x, this is the same. Okay, so if I now do the substitution, when eta is equal to 5, y is equal to delta f, the boundary layer thickness. So this is delta f and u infinity by nu x to the power 1 by 2, just cross multiply. And I'm going to take off this equation right here. Okay. So delta f is 5 times mu x by u to the power 1 by 2, which can be written in the form of the Reynolds number. So this is just, if I multiply and divide by x, I have 5x nu by that. Nu by u infinity times x is the local Reynolds number. Nu is mu by rho. So delta f is 5x and my question to you is, have you come across this in fluid mechanics? This is something that you would have seen and you would have used multiple times. And this comes from all of this hard work. Okay? So this is valid for laminar flow, flat plate, Reynolds number less than the critical Reynolds number, which is typically 10 to the power 5 for flat plates. And once you have solved for the fluid equations, we have to go back and do the substitutions into the thermal equations. Okay? I'll skip a lot of those details. So substitute for u, for v into the energy equation. All of these will still be functions of the similarity parameter eta, okay? So they will still be in terms of eta. You would have solved this equation to find f of eta. From this Blazy's equation solution. Then we post that T star is a function of eta as well. And this eta is obtained from the boundary layer equations, and eta is defined as the following. Once you do all of this, substitute this back into the energy equation. I'm going to skip all those details. We eventually end up with something that we're going to work with in the next class. Eventually. The story is half told, and in my words, this is half baked because I'm not showing you many of the details, but It is also from the point of view of general interest and time, this is a reasonable approximation. Okay? I'll be posting all these in my lecture notes. If you're interested, please go ahead, certainly. Eventually, which is something we could have written 3 lectures back without going through all of these things, this is what we end up with and this is what we want. We will end up with dt star by d eta at eta is equal to 0 as 0.332 Prandtl number to the power 1/3. Okay, so this is the eventual thing that we're going to end up with, and I have a few more minutes, and here is what I'm going to do. Very last step. So what do I do with that, right? Here is what I do. Flat plate. The first layer of fluid is a static layer of fluid.